Hello everyone and welcome to this presentation. My name is Niloofar Imani and on behalf of the co-authors, I will be presenting the research paper titled Hybrid Formation Tension-Based Assembly System for Bending Active Plate Structures. This research aims to develop a hybrid tension-based assembly system that enables the formation and joinery process of bending active plate structures by contraction of integrated cables. Bending active describes curved beams and surface structures that establish their geometry through elastic deformation of initially planar units. Due to their interesting formation behavior and added stiffness in their bent state, they offer advantages for fabrication, transportation, and generating spatial qualities. With the recent developments in the simulation techniques and computational design methods, new possibilities to form, find, and fabricate complex doubly curved geometries have emerged for architects and engineers. However, consideration of joinery and assembly of these structures during the initial design processes has grabbed less attention or is often neglected. This research contributes to the potentials of bending active by enhancing their design and fabrication process through the introduction of a novel, user-friendly assembly and joinery system. Conceptually, this research is inspired by the contraction cable approach. This approach is a FE form-finding method which was developed by Leonhard. By shortening the lengths of the virtual cables that connect the anchors of a planar plate, the elastic deformation is simulated digitally. Our research translates this virtual form-finding method into a physical assembly process. By defining and contracting the assembly cables, the initially planar units morph into their bending state and placement results in simultaneous occurrence of assembly and joinery. As a digital segmentation method, this research employs the form conversion method by Magna. Within this method, doubly curved geometries can be approximated to developable units by strategically removing material in high curvature zones. As a contribution, our research developed an iterative digital tool to define developable stripes out of resulted numerous discrete segments. The stripes are picked due to their overall material efficiency and maximizing the number of joineries per contraction, leading to optimized assembly. Since the definition of the stripes and exploring the optimal arrangement for the assembly cables are codependent processes, this research developed an evaluation feedback loop workflow. Within this loop, parameters that affect the assembly process are defined and evaluated. The digital process is initiated with the tessellation of the input geometry and eventually leads to unrolled ready-to-fabricate stripes. The result of the physical test optimized the workflow by updating the inputs for the stripe generation algorithm. The stripes are defined on hemisphere and cylinder as prototypical geometries, as these shapes offer regularity of geometry and defined radius and curvature. The rules derived from this test can be extended towards any doubly curved surface. The parameters are the surface absolute curvature, the deviation of the stripe in both global and local level, and the order of the assembly process. This diagram, for instance, demonstrates the process of generating test stripes with different deviation angles from a prototypical geometry. After the execution of the test, the following rules are attained. Regardless of the surface curvature, stripe deviation, friction, and material fiber direction, a limited number of joineries can be connected within one contraction. As the curvature increases in the input geometry, the number of contracted joints within one contraction decreases. This result can guide the users to define the density of the mesh in higher curvature areas strategically. In other words, a lower mesh density leads to a lower joineries. The angle of the stripe deviation has no effect on the assembly sequence. Two-sided assembly doubles the number of assembled joints within one contraction. However, depending on the anchors and the strip's location, two-sided assembly is not always practical as it requires space and defined contraction force vectors. Similarly, the rules were extended to other doubly curved surfaces. For each case study, a different stripe path logic was implemented. The logics were picked mainly considering the boundary conditions. This test is set to understand and evaluate the challenges of scalability and materialization which emerge in the proposed assembly system. The target geometry is a vertical multi-layered cantilever structural element with a 1.8 meter height and 0.5 meter span. To increase the structural capacity, a layer system has been proposed. Multilayering was performed through offsetting the shell to create material stiffness by generating a truss-like cross-section. The diagrams illustrate the correlation between the mid-layer bending radius, the offset distance, and the initial mesh density. The assembly process took place in less than a day. The main challenges emerged during the erection process of the stripes, especially in the initial assembly sequences. One of the prominent challenges was the stripe undesired deformation. This was avoided by using manual support to keep the stripes from excessive movements during erection. The other difficulty emerged in regards to the cable's contraction process, as no pulling direction and mechanism were defined. This paper suggests the potential of consideration of the assembly and joinery process in the early tessellation stages of bending active structures. Although it developed individual scripts, a comprehensive digital formwork from early form finding to fabrication is missing. In the realm of digital fabrication and parametric design, this research employed existing tessellation methods and developed an iterative digital tool to generate bending active stripes. The main focus was to explore the impact of the pure geometric parameters on the system. Therefore, it has been conducted material unspecified and studying material properties and precise analysis of the fiber direction, bending stiffness, and implementing these properties into early design needs further development. The combination of bending and tension elements and their effects on the system's overall force flows and structural stability needs to be developed further. This research contributed to creating material stiffness by developing a multi-layered bending active system that also offers architectural enclosure. Finally, studies on parameters that can decrease external forces such as friction can lead to studies on detailed design of contraction zones and strategic arrangement and placement of the contraction sources. While the proposed research does not suggest entirely replacing the established and conventional joinery methods, it simply broadens the future applications and potentials of employing bending active structure in architecture, engineering, and construction. As such, development of enclosure strategies can potentially lead to generation of user-friendly and mobile deployable architecture. Further studies on the tension cable's impact on the stability and reinforcement of the structure and enhancing the structure's load-bearing capacities can lead to generating formwork for shell structures. Finally, in conjunction with actuators, sensors, and motors to initiate and automate the contraction process, together with form finding and geometric studies, the system has the potential to be developed towards adaptive facade principles. I would like to thank the co-authors of this paper, Axel Körner, Riccardo, Magna, and Knippers. Also, my former research colleague Ahmad Razavi for his contribution to the research development. I would also like to thank my employer company, Werner Zobeck, for their support in my participation in the conference. And last but not least, thanks to the IASS Suri for organizing the event and the opportunity to present our research. Thank you very much for your consideration. I'm looking forward to your questions.